Okay, so today I'm going to go over a lesson on phase changes, and there's three major objectives I want to cover. The first is the different types of phase changes, and then the phase change diagram. And there's two parts of that phase change diagram I want to cover, what the different slopes represent, and also what the line lengths represent. And then finally, I want to cover a phase change energy absorption question and go over some strategy and tips to work through that question. Okay, so for the types of phase changes between gas and solid, we have sublimation going from solid to gas and deposition from gas to solid. And then from solid to liquid, we have fusion or melting. And then from liquid to solid, we have freezing. From gas to liquid, we have vaporization. And from liquid to gas, we have condensation. So let's see that in like a graphical representation. So here we have our phase change diagram with energy on our x-axis and temperature on our y-axis. So we're taking a look at what happens when we add more and more energy to solid ice. So initially, if we have that solid ice starting at a temperature below zero, that initial addition of energy goes into increasing the temperature of that ice. But once we hit 0 degrees, which is where the melting process occurs, that energy is continued to be applied, but all of that energy goes into the heat of fusion or the melting process rather than actually an increase in temperature. And then once the heat of fusion or melting is finished, any further energy that's added in this phase goes to increasing the temperature, increasing the kinetic energy of these liquid water molecules. And then here, this any energy that's added goes into the evaporation phase change. And we can see that the evaporation phase change takes a larger amount of energy because the difference between the liquid and the gas phase is much larger than the difference between the solid and the liquid phase. And this is because if we look at the properties, the physical properties of liquid and gas, there's a much larger difference because there are practically very few, if any, like intermolecular attraction or relationships between gas molecules. Whereas when we compare solid and liquid, there's still a lot of intermolecular attraction and relationships going because they're still relatively close together. So that's why our evaporation, the length of this phase is much larger because we have to apply a lot more energy to get through this phase change. Okay, so getting into a question, a lot of questions that they ask about phase change diagrams involve the amount of energy that is applied or the amount of energy that is absorbed by a piece of ice to go to either the liquid phase or a steam phase. So here we're taking a look at how much energy is needed to go from 5 grams of ice and bring it to a temperature of 20 degrees Celsius. Now, if we have ice at 20 degrees Celsius, that means it's liquid at 20 degrees Celsius. And there's 3 components to this question. First, we have the heating as ice, which we can see in this part of the phase change diagram. Then we have the heat of fusion, which is the actual melting of that ice over here. Then we have the heating as water for it to get to 20 degrees Celsius. And for both the heating portions, we're going to use this equation, the MCAT equation, but at heat of fusion, we have to use the heat of fusion of ice. And there's a couple things to note, and most of them are about the units. So in Q equals MCAT, our M represents the mass, which is in grams. Our C represents the specific heat, which is usually in joules per grams times Celsius. And then we have our temperature, which is always final minus initial. So when we plug in the numbers for the specific heat of ice is 2093 joules per grams times Celsius, and we plug in our 5 grams, and the heating as ice only occurs between 0 degrees Celsius and 5 degrees Celsius. So the final temp is 0 and the initial temp is -5. Okay, so this gives us a value in joules. And that's something that we have to note for later on. Okay, so now let's look at the heat of fusion. We have our 5 grams, however, the heat of fusion is given to us in kilojoules per moles, as we can see here. Now, this is different because in our specific heat, it was divided by grams times Celsius. So we're going to have to convert into moles before we can use this heat of fusion. So that's what's being done here. And then our answer is in kilojoules. which is important because our specific heat calculations gave us joules. So we're either going to have to convert this into joules or this into kilojoules. And I converted this into kilojoules before we add these all together. Okay, and then we also have to do the heating calculation for the heating of the water, and that's what we have here. The specific heat of water is 4,184 joules per grams times Celsius. And this calculation gives us the number of joules required to heat the water from 0 degrees Celsius to 20 degrees Celsius. And again, we're doing final minus initial. Okay, and once we have these three values, we can just add them up together. So 52.3 plus 1.67 plus 418 kilojoules will give us the total amount of energy required to heat this 5 grams of ice to 20 degrees Celsius. Okay. Now, there are a couple key notes about that type of questions. The first is that you must match units, so make sure that either your specific heat and heat of fusion are both in the same units or convert after using them. So make sure they're either both joules or both kilojoules. And then the second point to make is that with heat of fusion, it's usually in kilojoules per mole. So make sure you either convert from grams to moles, or if it's given in moles, convert from moles to grams before you use this specific heat, because it's in joules over grams times Celsius. And then finally, with temperature calculations, always remember that it's final minus initial. So with heating as ice, our final was from 0 degrees Celsius. Our final temperature was 0 degrees Celsius. And with heating as water, our final temperature was the final temperature given in the question. Okay, and so just to recap, the three things we covered today were phase changes, the different types of phase changes, the different components of the phase change diagram, and then we looked at a phase change question and we went over some strategies and tips. Thank you.